What's going on? Today, I'm gonna be continuing from like a stream I did a few weeks ago, reading this book, 259. So this book is called Advanced Digital Design with the Verilog Hardware Description Language. Shout out, whatever sport that is, like bobsledding. But back to 259. So left off on chapter 6. This is synthesis of combinational and sequential logic. My ambition is to finish like 3 chapters, and then perhaps look into some, like I bought an FPGA with a dev board, and I'm not really sure how to use some of like the networking things. Just as a reminder, I'm developing Pun Engine. It's a like FPGA accelerated trading engine per this. So a lot of these things with like the Phi, the Mac, and the TCP/IP stack, especially since like it's not going to be as plug and play as it might seem, because our TCP/IP stack will have to do some like proprietary requests that like set up they'll like tell the exchange that we want to subscribe to a certain data stream, and then also we'll be using like the second full duplex Ethernet port for like the TCP sending side, whereas the first one is for the like stream receiving side. And so, yeah, like not only am I not like the best Verilog programmer, like I am quite like a generalist and like a software generalist. Like I'm quite new to the hardware junk. So we got to like fix some skill issues, read some books. This is the second one I've read. Last month I read this one, getting started with FPGAs. That one was okay, but like a bit elementary, as the name suggests, and so I'm not really ready to fully build this, nor understand like the larger projects as a whole that interact with like many different IP and custom like networking cores. And so that's what the purpose of streams like this are to do. And I just realized that I was only on that screen the whole time. RIP. But yeah, this is Punt Engine. This is the diagram I was talking of. And yeah, getting started with FPGAs I read a month ago. And this is the book. This is what I was talking about, like bobsledding and such. But yeah. So, let me just make sure. Sweet. All right. Let's get into it. Chapter 1 identified the major steps of a design flow. Also, I was kind of thinking like me just reading like this, like somebody's gonna make an AI in like 50 years that's just gonna replicate my voice, and then like that's probably gonna be a net negative, but it is what it is. So yeah, synthesis engines minimize the set of functions that map your inputs to your outputs. We're not manually reducing K-maps. That's convenient. Understanding how to write synthesis-friendly Verilog models is the key to automated design methods. Makes sense? So synthesis tools perform many tasks. They detect and eliminate redundant logic, detect combinational feedback loops, exploit don't care conditions, detect unused states, detect and collapse equivalent states, make state assignments, synthesize optimal multi-level realizations of logic subject to constraints on area. Okay. So that involves, the last step involves optimization and technology mapping. All right, we're good. Synthesis. Circuit design begins with specification of the circuit's functionality. You have architectural, logical, and physical abstraction. So yeah, part of the appeal of using hardware description languages is that they transform your like more abstract or perhaps like behavioral descriptions of your circuit into the least abstract retro transfer level versions of your circuit. It's a net list of structural primitives. So this is called a Y chart. Represents how Verilog constructs supporting synthesis. It is a Y chart representation of Verilog constructs supporting synthesis activity in 3 views. The physical description is like as least abstract as possible. View. I'm not too sure what this says, but I don't find it to be particularly useful either. Translation engine creates an internal product of sums of a Boolean expression by factoring the sum of products form to expressions whose Boolean product generates the sum of products form. Translation engine creates an internal product of sums of a Boolean expression by factoring the sum of products form into expressions whose Boolean product generates the sum of products form. It factors the sum of products form into expressions Oh, is this supposed to say product of sums here? You're factoring the sum of products form into expressions whose Boolean product generates the sum of products. I don't understand that. Because if the expressions, I imagine if you're talking about a product of many expressions, I would think that to be a product of sums, or if you had a sum of expressions, that'd be a, either way. So if a product of sums representation for two or more inputs contain a common subexpression, the synthesis tool may minimize the internal logic needed to realize the circuit by generating the common subexpression once and sharing it. Okay, I mean, I think I get the principle. I shouldn't understand that sentence. UDP, but it means user-defined primitive. Multi-input, multi-output combinational logic circuit can always be optimized to obtain a set of Boolean equations whose input-out behavior is continued, whose input-output behavior is equivalent, while containing the fewest literals. I believe that. Software tools exist to perform this optimization and to cover the resulting Boolean equations by the resources of a technology library. Consequently, a Verilog description consisting only of a net list of combinational primitives without feedback can always be synthesized. Okay. Espresso is a commonly used software system at UCB for minimizing the number of cubes in a single Boolean function. What are cubes? Performs several transformations on a circuit to arrive at its optimal representation. I think I'm skimming that. So duplicate logic is condensed. Like, I understand this, that this occurs. I'm not too worried about how it works. I'm really just trying to write better Verilog. I do want clarification on this factorization. So I'm going to scroll back up. So we have an example. ABC, or ABD, or A naught, B naught, C naught, or B naught, C naught, D naught. So there is some duplicate logic. Decompose in terms of new terms x and y, xy, or x naught, y naught. X is AB and Y is C or D. So it's like pulling AB out of here, doing C or D, and then pulling B naught, C naught out of here, and doing A naught or D naught. So it's like pulling AB out. So it's, because the original expression was what? AB, ABC, or ABD, or, and just presuming by this, it's either AB, A naught, B naught, C naught. I thought it was B naught, C naught, D naught. A naught, B naught, C naught, or A naught, B naught, D naught. But this appears to be B naught, C naught, D naught. Because you're gonna have what? AB, C or D, or A, B. Oh wait, does the not apply? It's gonna be C naught, D naught, A, B, C, A, B, D, A naught, B naught, C naught. C or D knotted is not C. C or D not C or D. And not C or D. So it's gonna be not C and not D. Maybe I'm dumb. I'm satisfied skipping to RTL synthesis. Begins with the assumption that a set of hardware resources is available and that the scheduling and allocation of the resources has been determined. All right. Getting out of bed. Maybe I'm dumb, but either way, I think I'm fine skipping that espresso logic reduction part. Секундочку. All right, one sec. All right. All right, RTL synthesis. RTL synthesis begins with an architecture and converts language-based RTL statements into a set of Boolean equations that can be optimized by a logic synthesis tool. Begins with the assumption that a set of hardware resources is available and that the scheduling and allocation of these resources have been determined. Description represents either a finite state machine or a more general sequential machine that makes register transfers within the boundaries of the predefined clock cycle. So these descriptions in Verilog use language operators and make synchronous concurrent assignments to register variables. Right, so high-level synthesis is behavioral or architectural synthesis. Finds an architecture whose resources can be scheduled and allocated to implement an algorithm. It's only 6 p.m. It's super dark right now. It's kind of convenient that was like 8 p.m. or something. Resource allocation and resource scheduling. So data flow graphs display dependencies between data, and the allocation step identifies the operators used in the algorithm. Infers the need for memory resources to hold data applied by the sequential activity. So I feel like this makes sense. Scheduling the operations assigned to specific clock cycles, which are implicit states, to implement the ordered sequential activity flow. A compiler must form parse trees from statements and then extract a data flow graph from the set of parse trees. We'll see that in 612a. So you have a DFG, data flow graph, I imagine. Time-ordered sequential activity allocated to the clock cycle. So scheduling assigns the operations of the behavioral description to clock cycles. Again, talking about this data code. So let's just skip and look at this graph. All right. So I believe B was the data flow graph. All right. So clock cycle 1, fetch A and fetch C. I'm reading fetch in like a processor design context. I believe that's inaccurate. It could just be a prior state or just another signal in general. Either way, we add those presumably, and then we, looks like a tool, we mult the product called A and the fetch E, producing D, and then we take A and D, extract it and store that in M. So this right one is like breaking them into clock cycle lines, whereas the left one is parse trees. Okay, so this is parse, yeah, okay, that makes sense. Parse trees data flow graph. So synopsis is behavioral compiler. Okay, whatever. So synthesizing combinational logic. So there's many ways to describe it, but not all are supported. So in order to be synthesized, it must be a net list of primitives. So we have a pre-optimized schematic of bool opt. And then I believe B has less area, so it's more efficient. So bool opt, not sure what it does off the top. But perform some function, and its truth table effectively is just made more efficiently. So yeah, level sensitive cyclic behavior will synthesize to combinational logic if it assigns a value to each output for every possible value of its inputs, because otherwise you need to just latch onto it, because it's going to assume that you want it to be the same. And this implies that the event control expression must be sensitive. Yeah, seems legit. So we're doing a OAI 22A and a NAND 2IA. All right. We have a 2-bit comparator, sensitive to A or B. Then we do this compare loop. We're just writing a comparator. So we're trying to show that. So let me just not skip ahead and actually read what they're saying. Describes the functionality of a 2-bit comparator by level sensitive behavior. True. This algorithm exploits the fact that the data words are identical if all of their bits match in each position. Okay. It's not as simple or as elegant as the ones in chapter 4 or 5, but it serves to illustrate the power of synthesis tools to correctly synthesize combinational logic from a level. Oh, okay, yeah. Okay. So when this is synthesized, you'll find no latches. That is kind of curious. Though I don't really see the appeal of, like, I imagine this is more of a point. Because, like, I don't imagine you would want to write a model that, like, implies sequential logic that doesn't actually require it. This chapter, like, I don't feel like this chapter was really helping me that much. Like, I still understand that, like, oh yeah, synthesis tools, they are minimizing the area of your combinational logic. But, like, that's what I'm really taking from this. Okay. So a synthesis tool will treat mutually exclusive conditional statements, perhaps conditional expressions is better, as mutually exclusive and synthesize them as a mux instead of a priority structure. Interesting. So some exploits for don't care conditions. So if you assign to X, so I've been writing a lot of VHDL. What is X in Verilog? Verilog X. X is, so Z is impedance. X is don't care. Yeah, I recall that. So, skimming a bit, if a conditional operator assigns the value Z to the right-hand side, it will be a 3-state device driven by combinational logic. 3-state device. assigns the value z to the right-hand side. I think that makes sense. Yeah, okay, yeah. So, sequential logic with latches. Latches are, yeah, either intentionally or accidentally. Okay, this is important. You don't want to accidentally make a latch, so let's figure out how not to do that. Now, list of primitives, Boolean equations, or level-sensitive cycle behavior. A feedback-free netlist of combinational primitives will synthesize into a latch-free combinational logic. Say it again for the people in the middle. So the preferred way to intentionally model a latch is with this conditional operator with feedback. Oh, this is the, like, ternary. That makes sense. Because one of them, the latch will just preserve the state over the next clock cycle. Accidental synthesis of latches. Or for behave, it's a 4-input OR gate. So we have a latch in our OR gate. So we have a parameter 4, so the output is y. The input is a vector 4. We have a reg y and an int k. So on xin, check for 1. So this sets our register y to 0. If 1, this is like an algorithmic description for all the bits in this vector. If any one of them is 1, set our register to 1, disable check for 1. So this is fine, no latch. So on the one that's not sensitive to xn of 0, this synthesizes a latch input. So let's consider why this synthesizes a latch input. This is kind of odd. Because we're never even reading xn of 0. Well, oh yes we are, because, yeah. We are because we still, that is actually kind of curious. Yeah. We still like go through each of the bits in this vector, in this like 4k equals 0, k less than or equal word length minus 1. But we don't actually have the 0th bit in our sensitivity list. That is a bit curious. To avoid latches, all of the variables that are assigned value by the behavior must be assigned value under all events that affect the right-hand side expressions of the assignments that implement the logic. So they're saying that since the so behaviorally a change in the 0th bit of xn implies a change to y. But this is not the case as described here. Still considering like, why does this make a latch? Hmm. If any of these inputs is 1, the value of xn of 0 is passed to the OR gate. Why is it latched? So, if the output of combinational logic is not completely specified for all cases of the inputs, then a latch will be inferred. Huh. So it synthesizes to this. So what does this do? Three, two, one, or those. That enables the passing of. Huh. Okay. So having this as either the ORs here or the enable of xn of 0 enforces that these are the only entries in the sensitivity list. So you can only allow xn of 0 to affect the output of y on a change of xn of 1 of 3 down to 1. And so like how do you do that? Well, you have to use the latch to enable the passing of x0 into the OR gate producing y. Okay, I think that's legit. That's helpful. Okay. This is why you use Haskell and Clash, bro. Okay. I'm gonna just skim 3-state devices. We can read this. So they allow buses to be shared among multiple devices. True. So yeah, I use these. Yeah, you have a register file. Unidir bus. So if bus enabled, write your data to the bus, and you're not really reading from the bus. Circuit shown in 628 has a bidirectional interface. So yeah, you have a receive data enable that opens this buffer for you to. Oops, I don't know what the verbiage there on like open the buffer, like allow the buffer. I'm just gonna say opens. That's possibly wrong. It could also be the complete contrary, and where you're supposed to say close. But yeah, so it allows the buffer. It allows the passing through the buffer, whatever. But yeah, send data is a write enable. Okay. So what does this look like in Verilog? It's actually good to know. So you have data to from bus, send data, receive data. These are enables. So in out, data to from bus, input, send data, receive data. 2 wires, CKT to bus. Data to from bus, data from bus. Хорошо. So assign data from bus is equal to receive data. If receive data true, data to from bus, otherwise a 32-bit vector that is high impedance. And data to from bus, well, if send data is on, it's going to be reg to bus, otherwise data to from bus. So this is like intentional synthesis of a latch, I believe. Sequential logic with flip-flops. So these are edge-sensitive cyclic behaviors. They are clocked. Synchronized by a clock. So what defines these from like the perspective of synthesis? What causes these to be synthesized, perhaps? So if you're in a edge-sensitive context, then the things that we were talking about before were incomplete if and else statements that don't fully map inputs to outputs would just latch the inputs to just like preserve them, or like latch intermediates to preserve them. In the edge-sensitive case, it just creates a clock enable. I believe that. A variable that is referenced within an edge-sensitive behavior before it is assigned value in the behavior will be synthesized as the output of a flip-flop. Variable that is referenced within an edge sensitive behavior before it is assigned will be synthesized as a flip-flop. That's not obvious to me, so let's read this. The non-blocking assignments to data A and data B and swap sync. I've never seen sync with the H. Describe a synchronous data swapping mechanism. Statements assigning value to data A and data B execute non-blocking assignments concurrently so that both variables are sampled before receiving value. So that must be the output of a flip-flop. Set 1 and set 2 are explicitly decoded first. The last clause of the if statement assigns values to data A. So these are going to be on the rising edge of a clock, which is not referred to explicitly in the if statement. So let's see it. So output, data A, data B, I believe it. Input, clock, set 1, set 2, and swap. I'm not sure what these inputs. So clock, set 1, set 2. I'm not sure what swap is. Let's see. So on the positive edge of the clock, if data A, so if set 1, set it to, oh, so these are like 3 modes. One of them sets data A to 1, data B to 0. The other one sets data A to 0, data B to 1. The actual, so otherwise I imagine it's swap because we're not even referencing that at all. But else begin data B, swap data A, swap data B. Or perhaps, yeah, that's happening at the same time. So this implies a flip-flop. Makes sense. So what does it look like? Variables referenced before assigning value. Okay, yeah. Four-bit parallel load data register. So I'll read the tips. A variable that is assigned value by a cyclic behavior before it is referenced within the behavior that is not referenced outside the behavior will be eliminated by the synthesis process. Fair. There's a point to realize that not every register variable that is assigned value in a cyclic behavior synthesizes to a hardware storage device. Register variable K is not referenced. It merely supports the algorithm. Yeah, okay. Yeah, that makes sense. And a variable that is assigned value by an edge-sensitive behavior and is referenced outside the behavior will be synthesized as an output. The behavior in empty circuit assigns value to the register variable dout, but dout is not, so it's eliminated entirely. So it, okay. Synthesis of explicit state machines. BCD to XS3 code converter. It's a merely binary coded decimal to, okay. I'm not too interested in this. More type NRZ to Manchester. Not too interested in this as well. I think I would learn more by just doing something than reading that. Registered logic. Variables whose values are assigned asynchronously. Sorry. Assigned synchronously with a clock signal are said to be registered. They're updated at the active edges of the clock and are stable otherwise. Yeah, I'm really not feeling this chapter. Not really too interested in this for my use case. Yeah, I think I'm just gonna default to skipping this. Design and synthesis of data path controllers. See, I'm not too concerned with synthesis. What is this on? Alright, I might come back and read this, but I'm just gonna go ahead and jump into just writing stuff. Content. So, let's make this bigger. Let's open up Vivado. I really need to download Vivado 2023. I should probably just go ahead and do that. Download AMD Vivado. We can try doing this project in 2024. I should remove this, and then I want Vivado on the third one. 1, 2. Why did that go? Dude. 1, 2, 3, 4. Alright, let's go to the bathroom, so we're gonna make a new one of these. Let's duplicate this scene, call it bathroom. Let's get a toilet PNG. This one looks solid. I think you're gonna need to save the image. You can put that in doc. We can make a new folder. Oh, we already got one. Image. Toilet. Toilet one. Let's go in here. Let's add an image. Toilet one. Image file. I'm gonna put it in doc image. Huh? Where's it at, bruh? Is it a .webp? That's a .webp, bruh. Is it a? It's a vector image. Alright, let's just go for this one. It's a JPEG. Toiler one it is. Here, toiler one. Okay. Let's do this. Let's do that. Let's get a text box. Is there not a text box? There we go. Free type 2. Let's just make this. What is this going to be called? Bathroom. Huh? Toilet text. Looks like a fine font to me. Text. Bathroom. Let's get a poop emoji. Satisfied with this one personally. Poop. Here. Add. Image. Poop one. Browse. Poop. Open. Apply alpha in linear space. Let's do this. Let's do that. Okay. Oh, let's add break. Let's I honestly it should be easier to add a new text box. Let's break on it. Bathroom. And it's editing the previous one. Remove that. Yes. Toilet text. That one can be bathroom, but we're making a new text called break. 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 Move that. Okay. Alright, one sec. I'm just gonna throw away the box. Shout out. Whatever that says. Actually, I'll probably keep it. That's kind of it's gonna be painful trying to move this. I'll put this. Alright, let's. You gotta queue up a piece of pumpkin pie, bro. 1 sec. All right, I might have to get on the phone again in a second, but we'll see. So I left off. I was just like, all right, let's actually start doing something. So opening this up. So this BDF is going to be huge, or BD in the case of Xilinx. Turn my finger around. All right. Kroger pumpkin pie is kind of weak. So, so I might try to finish this. So this circuit is a accumulator. It's actually not going to be particularly slow nor fast. Because it is a moving average accumulator. And so it will record the moving average over the last 2 to the n samples, where n is like a constant passed into it. So I was trying to do it with this. I'm gonna have to fix my cabal fast. So this is just gonna be moving average. Let's go to accumulators cabal. That was accumulators cabal. Let's go to cabal project. Is that it? Moving. Okay, so this is gonna be moving average. Fast. Moving. What about search grab it slow moving? So, okay. So it has some type errors. These were kind of annoying. Takes in ints and it puts out ints. First of all, it shouldn't be taking out an int. It should be taking in a yeah, I guess the int will be the price in cents. Yeah, I was really not sure how to do this. I was trying to use like a circular buffer. So like you can imagine, like we're accumulating an average over the last 2 to the n samples. But like you don't want to recalculate all of them at once. You want to like divide the last one out. Like subtract the last one out and add the most recent one in. And so like, you're going to be comparing a fast moving average to a slow moving average. So like a moving average over a short time sample, or in this case, with a low n to one with a higher n. And so imagine if we had 2 internal wires. I almost just want to write this in Verilog. Honestly, I might just write this in Verilog. Let's try it. I need to download a Vivado 2023 one. All of like the IP is for Vivado 2023 one. Give me the Linux bin. Welp. That's why you don't use your real address. Let's go to the bathroom screen while I remedy this. No, that's actually good. Put this in DEP, I believe. 2023 already exists? Really? I have to make a terminal here. CD here. CD, we're gonna make your Photo 2023 1. Move Xilinx unified into Vivado 2023 1, CD Vivado 2023 1, unzip. Or I think we just run it. It's the only thing in here. Chmod plus X dot such thing. Such thing. Please work. There we go. So yes, I'm not using Red Hat Enterprise. Okay, wait. Did I go back yet? Okay, I'm gonna log in. What is my... I just want Vivado. Standard. Alright, so... Give me the... I think we're good there. And not right there. I'm gonna need to sudo this. You're waiting that long to tell me to sudo this, dude. That's kind of annoying. I already have the latest. Downgrading intentionally. Next. Just Vivado. Not Enterprise. Yes, I want all that. Besides the MATLAB junk. I don't want DocNav. I agree. No. I agree. Tools, Xilinx. 2023. Create it, install. Off that screen, off that screen, off that screen, off that screen. Okay. Alright, so installing Vivado bricks OBS. So we're just gonna keep using 2024. Oh my gosh, it jump scared me. Oh my gosh. Okay. So Still don't understand what this junk is. Let's just remove this entirely. Let's add a new design source. It's gonna be a new file, Verilog file. Maybe I should do system Verilog. File name is gonna be moving average. .sv. Sweet, so this exists. Moving average .sv. So, been writing a lot of VHDL. How do you write Verilog? This might be. Just make sure I don't expose IP while I do this. This might be a good util for Jippity. Just some boilerplate. So. I'm writing a Verilog core is a moving average accumulator. Or moving average accumulator. Takes in a constant number, n, that defines the 2 to the n last samples last clock cycles to accumulate on. Takes in a stream of numbers representing orders how do you wait? Yeah, so that actually raises a question of like, how do you even do this? Because we might have an order book, might not. This probably takes so much fabric. So I'm going to rename this. Can I also like make this bigger? I know this is like probably impossible to read. Smelling very smoky from the kitchen right now. All right, I'm gonna show you rename junk. So what is the pound here? We have the pound symbol. Oh, these are parameters. Okay, parameter integer n equals 3. Okay. Parameter integer data width. That's important. Data width. So go to 16. It's gonna be 16. I am actually unsure. This is wrong syntax here. This is comma nothing. We tab over, tab that down. Is there a Vim mode? Right. We're just going to open this in Vim. So Q. We're in here. Vivado. No idea where this file is. No idea where this file is. Let's look at GitHub, HFT. How are people structuring this? This is just a link to. Okay. Oh, okay. They're doing theirs in C. So this is where they're talking to the FPGA. Yeah, there's so much going on in these systems. So it has source. It's got XDC, TCL. Either way, I agree with these. But yeah, where are you putting this junk? I'm curious what it thinks here. Yeah. That is probably a better setup. So we're just gonna get. This is so much, dude. Doc stays. We're gonna have Vivado stay, kind of. Rename that DMA lib. We'll have HDL in general, within which we'll have SV, keep, v dot slash v slash dot keep. Let's do Haskell slash source. I like that. Source, keep, and then generated, keep. Let's go generate source, SV. Let's just assume it's Haskell and SV for now. So this should really be a COBOL project that has a bunch of within it. So honestly, let's make a new COBOL project in there. Then let's honestly make a new Vivado project. Or we can do a project. And then go in here. Vivado, move all of this into this. That's gonna break this. Let's bring cross that out. So then we have Punt Engine Vivado project. The other Vivado is scripts, constraints. Okay, let's just do constraints for now. New folder constraints. So back in here. Vivado constraints dot keep. You have project, HDL Haskell. You have docs and you have DMA lib. So accumulators. Just gonna rewrite these entirely. Docs, DMA lib. Fix parser. So let's go into LS. Let's go to CD HDL, CD Haskell, LS, CD source, LS. And then we're gonna go to / Haskell. And we're just going to set up a project. So what is the command for that? Wait, we go to /lang, /starters. We can just use stack. Call it Punt Engine HS cores. Punt Engine Haskell cores. /lang simple. LS CD Punt Engine Haskell cores. Move start out of /start. LS CD dot LS RM RF Punt Engine Haskell cores LS. Is there like a diagnostic thing we can do here? We can do clash build. We can do a couple wall dash clash. Let's read the README. I swear this used to be longer. It's because you got to go into simple first. So stack build, sorry. So while that's going on, let me get a water. Hasn't crashed yet. That's impressive. Clean the pumpkin pie. Let's put the nip drawer. Happy holidays out. Open that. Put the lid. RIP headphones users. Move that. Move that. Script this. There. Move that. Massive compilation of Clash Lid. You love to see it. Put the slippers on so you know I'm not messing around. Let's water the orchid. Maximum productivity. Let's go in the clock. Let's give that 20. Let's do 24 minutes. What's this about to do? Oh my gosh, that worked. Wow. Actually impressed. So we have that initialized, and that leaves us with what structure? Get Nautilus out. So NHDL, Haskell source, bin, tests, all that. So source example, we're gonna add source fixed parser. Yep. Sorry. That's good. How we do this. So you get example, and then project.hs. I think it would be better to do source, not rename, new, source fixed parser top, fixed parser slash top.hs. I think that's quite reasonable. Let's yank the data in here, paste, example. I'm fine leaving example. And just leaving the rest of that, but also adding that. Hunt engine, XC clash, test library. That's fine. Stack, that's fine. This is what changes because we add in. So we'll have test example project. Nothing else exists yet besides expose modules, though this is not really a library. Consider this an executable. Or I guess it is a module because the executable is clash. So it's fixed parser.top. Or else we have example dot project test example dot project. So I think that's fine. We can update this to MIT, DT caret, Race Williams. Okay, I think that works. Meaning we can just, we'll yank this. What is this? What is that? I do not remember having that. I do not remember having that. What is that? There's like some type of GG0VGT. Yeah, that's kind of tripping me out. I don't really like that, to be honest. We have an error in fixed parser on top. That's as expected. So there's HDL. There's still a gatekeep in here. No gatekeep. Yeah, there is a gatekeep. The source generated. We can keep a gatekeep there. It actually generates to dist new style. Maybe that's false. SV. So in SV is where we'll have this. So all of that to say that we'll have. So this is a script TCL. Oh wow, that's kind of convenient. Wait, what is TCL? TCL lang. Tool command language. Okay, let's just do it. Script slash. It's saying there's a create project.tcl. That looks quite convenient. So I'll just trust that blindly. Add Verilog sources. Add system Verilog sources. Add class generated sources. So we change this to Haskell. Add constraint files. Set top module. My top module of current file set. And then you just run it like that. Say less. Build automation. Having this would be nice. I'm not sure what's committed to Git right now. Not the... So. This leaves DMA library, docs, important stuff stays, Haskell, SV. So we can go ahead and SV. Alright, I'm quite impressed with that. I'm impressed with that. So just blindly to start an SV, have a moving average accumulator.sv. Just paste that just to get rid of the git keep. Auto constraints, git keep project. So honestly, delete that project because we're going to remake it in 2023. Project.git keep. Scripts, we have a script there. Let's do it. To do, define my top module. What is my top module? License MD looks right. README MD looks right. DMA lib include source tests test pattern.c docs if docs HDL scope generated git keep auto constraints no constraints project my project create project.tcl. Let's just get out of that and get combination that reorg TCL create project. So let's just see what that looks like. We're on a bit of like a, we're doing some kind of useless stuff currently. So I just want to see this branch. So if auto init, like I just want to check this branch out. Is TCL Pascal? Like, why is it saying Pascal? Pascal file extension. Pass obj exe. I mean, he's talking largely about pass. I don't think we have anything about pass in here. What is the Pascal? OPR. It's in Vivado. Does that even exist? I don't think it's updated this. Yeah, it's because it's on the master branch. Okay. So I'm safe to just, I'm confident to just do this. So when you do all that, you do git switch main, git reset hard, git pull. You can delete these stale branches, honestly. Just clean these up. It's already merged. So I think we're good there. The main branch. So Cloudflare deployed. We have this is our DMA lib. So that's been broken because the host DMA lib. So this is the job. We'll call this DMA lib test. And this is now called DMA lib. The binary, what is the binary called? DMA lib build, like DMA lib, name DMA lib, test DMA lib. So we're going to delete D, const DTD, go to DTD. And we're going to, okay, we can just rename this at this point to DMA lib. And that broke everything, so we're going to go back, rename DTD, DMA lib, enter. There we go. Test. It's not a string in here. So then we're going to go into my GitHub workflow CI. Just gonna, or we can just redo what I just did. So add the name of CI, unpush domain and unpub branches, build and test. So DIW. So we're gonna call this DMA lib test. Back to latest, and then like we just did, DTD and DT. We can do DT. So okay, I think that's solid. Just git add -a, git -m, patch, DMA lib CI test, git push, git pull. Go to the repo. That's fine. And expect this to succeed. So I did something, not convinced that's necessarily productive. Let's do something else. And let's make that something else writing this. Gzip system Verilog. Verilog SVLink server. Let's just use SVLink server. Okay, so let's remove all of this. Module moving average accumulator. So we have parameters. So let's look that up. Verilog parameters. This is the ANSI style. So I agree. Have a parameter integer n. Call that 3. We'll have another parameter integer data width. Just act like it's 16. Likewise. Yeah, I don't understand this like indentation at all. Likewise, in here we'll have input, logic, clock. We have a clock, we'll have input and logic. reset, or is it RST? We'll have input logic. So this is a signed. Why? So back to the accumulator. Why is the in and out signed? I'm also curious, so yeah, that is right. How long have we been on? 2 hours? It's probably like 8 p.m. right now. I don't imagine these will be price changes. -1. That's false. I understand in order to do subtraction safely, you must have signed. But, oh no, because the subtraction is not on the values, it's on n. No, that should not be signed. So, Verilog signed. Well, let's first just see if it compiles with unsigned. So this is from ACC with -1. Where was that defined? So we have a clock, we have a reset. We have an unsigned, yeah, this must be unsigned. Data width -1 to 0. DN. We're gonna have input logic unsigned. Data width -1 to 0. Yeah. Okay. That makes sense. We'll have a in module at the end. And then in the middle. Is there, so you don't put a, you not put that after that. So we'll have local parameters. Local params. Local param. So I don't imagine we need to comment local parameters when it says local param. So integer, so yeah, I agree. Big N, whoa. Big N is 1 left shifted N times. I agree. So it wants that local parameter integer ACC width is equal to data width plus N. Width of the accumulator to prevent overflow. I see. So the accumulator would never be negative. This is additive. Wait. Yeah. That is a good point. Yeah, it should be signed. Because local params signed. Sorry, this is logic here. Signed ACC with -1 to 0. Accumulator. Just call it ACC. We don't have a logic signed. Data with -1 to 0. The sample buffer. I'm gonna need more explanation on this, but it currently knows better than me, so I'm gonna trust. Always FF. What's the difference in that and always? Flip flop. Alright, that is the alarm for my water. 1 sec. What a catch. Okay. Yeah. Sample buffer. I don't think you need it. That. Yeah, you do, because you gotta divide the last one out. You gotta subtract the last one out. Always FF. This is on the pause edge clock or neg edge reset. Pause edge reset. Okay, again. And so if reset begin, we're gonna hit end, else begin, and if reset begin. So you can imagine what's happening here. Accumulator. This is kind of aids. It's a 0 array, 0 vec. D out, 0 vec. And then 4. So we just reset the sample buffer. Zero, that's the big N, plus plus. Again, and we do sample buffer at position I, 0. Okay, so in this, that means it is the pause edge of the clock. So what do we do? Subtract oldest sample and add new sample. I agree. Subtract oldest, add newest. ACC, we're going into, so this implies a flip-flop. ACC minus sample buffer, and -1 plus BN. Yeah. Shift sample buffer to make room for the new sample. Okay, shift sample buffer to make room. Maybe this gets for the next sample. Yeah. Or no, it is for the current sample. So how do you do that? Is this gonna have to shift everything? I'm not convinced that's the best strategy. I'm really curious what this synthesizes too. And also, just right at the end here, we're doing a... Yeah, okay. And then D out, send to ag, shifted n times. Big brain. That's actually good. That's actually quite good. No, that's like what I was trying to say, honestly. That's kind of smart. Yeah, ChatGPT might be solid. So it compiles. So compute moving average by dividing by 2. Wait, so shouldn't this be big? What's the utility of big N? That's for the like the sample buffer. That's solid. No, I messed with that. Alright, so we have this. Alright, so that exists. Wow. Dang, that's impressive. So was this a modification? No. Alright. So we're in here now. We should also get checkout -b this to moving average. So this has been resolved in direct commit. So I'm going to make a new one. It's going to be create moving average accumulator. So this will be in enhancement. This will be in progress. I'll assign this to myself. And add this to a new milestone. Accumulators. Okay. That's solid. And then I don't think they should be alphabetical per se. Maybe they should. So there. Back to Pun Engine. Okay. So we have this. Error during time, not in gzip format. That's kind of annoying. So we have this. So let's just be lazy. So the other thing is we're going to be using Xilinx 2023. Probably specify that we're using Xilinx 2023. I might save that for another stream just because it's going to be impossible to stream while downloading Xilinx 2023 because it just breaks my FPS. Okay, so I might just pause this and go back to reading for that reason. I'll finish this chapter and maybe another one, then I got some stuff to do. And I think that'll be a satisfactory setup. So did anything change here? Git diff. It did. Okay. So what was I about to do? I was about to git diff this. I was satisfied with that, so I'm gonna git add dash a git commit dash m moving average. untested, end quote. Linter.vc. nvim SVLink server linter.vc. Okay, we need to add that to git ignore. Dot nvim. Git rm dash dash cache dot git. Need r git dash a git commit dot m dash m remove dot nvim. Git push dash dash set upstream origin moving average. Okay, so refresh. So that works. Patch DMA lib CI test. Okay, this is looking kind of legit. Looking nice. So, design and synthesis of data path controllers. Digital systems range from those that are control dominated to those that are data dominated. Control dominated are reactive. Data dominated are high throughput. Signal processing. Sequential machines are commonly classified and partitioned into data path units and control units. Most data paths include arithmetic units. Data paths consist of computational resources. Often modeled as finite state machines. Repetitive operations on different sets of data. Yeah, I'm not a big control unit fan. So you're just separating your control unit and your data unit. So you have a finite state machine of the inputs, and that controls the data path logic and the data path registers individually. Or these are perhaps representing the same clock, actually. So a control unit generates the load, read, and shift contents of the storage registers. Fetch instructions and data from memory. Really? Yeah, I agree with that. That makes sense, yeah. So you got a bunch of charts. You have an application. So this is like processor design a bit. You have your architecture. And your wait, what am I trying to say? So the very beginning of chapter 4. Let's binary search it. 200. Too far. 140. Too far. 130. No. Is it architecture and organization? This is like quite a mute point. Rip. That was a waste of time. Design example of binary counter. I mean, so yeah, you can design this a bunch of different ways, and these charts show that. RISC stored program machine. So we have these controllers. Yeah, I've kind of seen this. Already. Yeah, I'm not too concerned with this. Maybe I will do a stream building a RISC processor in Verilog as an exercise. Yeah, I'm confident to skip this subsection. Program execution. Let's get some. So UART. Yeah, I'm satisfied not knowing much about that. Yeah, I don't really care about that. It's not really what I'm looking for. These are just the exercises. I expect no difference. So this is talking about FPGAs. What time are we at? How long is this chapter? 441. Okay, that's quite. Oh, I was skipping way faster than that. 441. Let's go to 460. Alright, 441. I think I'm gonna end it here, honestly. So I know like on the reading portion, I kind of just skipped everything. But I think it's fine. Like I kind of got what I wanted from those chapters, even when that was next to nothing. And we restructured that. Like super useful, but it's like a bit of a side quest. So yeah, just gonna end it. Put it on the bathroom screen, and then when I see it here, just so that it knows that I've said everything. Alright, yeah, that's it. So yeah, this one was kind of lame. I didn't really do anything for real. But, yeah, it is what it is. So yeah.